valid ones with, replace one of the other statement tokens with another valid statement ID that we know of that doesn't belong to us, belongs to another user that we have access to. Change that field, leave all the other stuff the same because we don't know what it stands for anyway, and view the contents. Didn't work. So we're forced to go back and try and understand a little bit more about the structure of that token. The first thing people do to usually protect against you messing with the tokens like that, other than the encryption, is an integrity check on the plaintext. So we're thinking maybe this, maybe these letters at the end are some sort of integrity check against all that other data. So that if you change one of the bytes of data in the earlier part, you've also got to maintain that integrity check on the end. Otherwise, the application is going to calculate it and determine it doesn't match. Someone must be messing with this. Throw out the request. So at the end of each token, we see 4 letters, look like base 64. 4 base 64 encoded characters equate to 3 actual decoded bytes, or 24 bits. Thanks to Google, it turned out that this was a standard CRC24 algorithm, which you just searched for and found the reference code. It was about, 10 lines of code or something in C, and just ran it through, just compiled it, and threw in one of the plain text tokens and see what came out. And it was CRC24, reference implementation. No secret in there or anything. I mean, the CRC is intended, for transmission errors and things like that, not so much for prevention against people manipulating stuff. Because if there's no secret there, it's just a calculation that I have to make. It's not really protecting very much. So now we've determined that we've got, in a given token, we've got plain text followed by the CRC24 of that particular plain text, base 64 encoded. So, so this is kind of our step-by-step how to build a token from scratch. So you generate the desired plain text of the token. What do you want to be in there as your plain text? Or manipulate an existing token, like we took a statement token and just changed the parts of it that we wanted to change, and leave the rest intact. So somehow we come up with a plain text version of a token. We calculate the CRC24 of that plain text using our reference code and append it to the end of the token in base 64 encoded form. So those 4 characters that we saw before. Encrypt the token by performing an XOR of the plain text with the key stream that we recovered in the earlier steps. So that's our process of encrypting. And then finally, base 64 encode that encrypted token so that it's in the same format as what we originally saw. And when you do that, you can see other people's statements. You can view files on the system. You remember the file parameter. Not any file. I think we were constrained by permissions, but still, you could see a bunch of files that you shouldn't be able to see. And we were able to manipulate the application in a number of different ways by virtue of being able to just construct tokens that the application was considering as trusted, because they felt that the crypto couldn't be broken. So the recap. Again, we were able to successfully subvert the encryption mechanism without any knowledge of the algorithm or the key. Like, think about that for a minute. Like, it's actually kind of cool. Like, you don't have to know anything about it. Like, you just look for some patterns, and you've broken the crypto. I don't know, kind of cool. It turned out that it was RC4, and that was more for kind of our curiosity than anything else. What is this? Are you just XORing with a static string that's hard-coded in your app, or are you using real crypto? So they're using RC4, and they were generating a unique key on every user session, which doesn't matter to us because we can just go through that same process for a given session to figure out what the key is. And actually, once you know what the value of one of the really long tokens is, you don't have to go through that whole iterative process. You just look for that one, and then just generate the key stream based on that one piece of data. So the failings here are the reuse of the key stream across many different tokens that are used for completely different purposes, and the lack of any sort of integrity check. the CRC24 is not going to do it because there's no secret involved there. So that was breaking a stream cipher. Let's check on time. We might actually make it. So third case study. And this one, I'll say up front that there is no crypto in this one whatsoever. We've done the block, we've done the stream, but this is, you know how we talked about making up your own stuff, your own algorithms and your own crypto and security through obscurity, basically. So that's kind of what this example is, but it's kind of a fun one. And the important thing is that the techniques, just the sort of observation, pattern recognition, analysis techniques are the same as in the previous two cases. Okay, so here's an application we're looking at. This one was a retail application. So in your profile, you had information stored about you and your credit card and things like that. Through a separate vulnerability in the application, different SQL injection error, we were able to dump the contents of the database. Hundreds and hundreds of tables, but these were the ones that were interesting. So you can see that that one table contains maybe a number and some stuff about me, and I should have changed my email address before I switched companies. The shopper table is the one that kind of looks interesting because you see the word Visa in there, and a bunch of dates and a bunch of asterisks that usually used to mask out credit card numbers and 4 digits, and I don't know. It looks more interesting. Definitely some privacy and compliance issues when storing credit card numbers if there's any way that they can be recovered easily. Anyway, so we try to break down that data. And the credit card that we had stored in our profile was just generated using one of those tools that just generates credit card numbers that satisfy the mod 10 requirement for calculation. So in the database, that particular field that ended in Visa, that's the one that we're looking at. So in the database, when we changed our credit card to that, we saw that. So we can kind of clearly see where the expiration date is at the beginning there, because that's the expiration date we put in. And we can see what the last 4 digits are that match up there right before the word Visa. But the stuff in the middle, what is that? It doesn't seem to correspond to the original credit card. I mean, I don't see any obvious mappings there. So we want to figure out kind of what that is. So we changed our card number to 4 and all ones, which is great because that's sort of the simplest form of the credit card number that still passes the check, and it's what all the applications typically use with testing. But anyway, so we changed our card number to that, and then we checked what was in the database after that change was made, and then repeated this process like a bunch of times to see, first of all, is it the same in the database every time I change it for a given card number, or does it vary? And as you can see, it varied. It's the same card number going in, and the stuff in blue on the left and right is the same, the 4 digits and the expiration, but the stuff in the middle changes. And take a look at all the ones that sort of appear in the unknown section. Well, that definitely maps to the plain text, and maybe that wasn't as evident in the previous case because there was just a varying distribution of characters in the digits in the original card number. But now here, clearly we see a pattern. And if you count up all the ones, it adds up. And there's just some other garbage that's being sprinkled in there, and you can see that even the garbage appears sequential. You can see 1, 2, 3, 4, 5. It's just the positions at which those pieces of garbage actually appear. So, this suggests that what we're looking at is some sort of transposition, a reordering of the original digits. So we've got in the middle section there, we've got 30 digits, and the credit card is only 16 digits. So we have to figure out what's real and what's noise. So we scripted up the credit card number changing operation and retrieving the value from the database, and did that a few hundred times. And Upon looking at the data a little bit more closely, we saw some patterns that kind of came out with relation to the two characters coming right after the expiration date. So we noticed that anytime those two characters were 04, there was a kind of a commonality in the structure of the transition, or the way the data appears in the red section. And similarly for 44, 65, and any other digit between 00 and 99, we saw kind of a pattern of, hey, look, most of the ones appear in the same place. So right there, all of the digits in the original card number are highlighted, so are bolded. So all the 4s and 1s are bolded. So you can see in most cases, so take the top block, the 04 block. In most cases, the bold sections appear at the same locations in each of the 3 examples. There are a few cases where they don't. So that's going to be a case of, well, am I looking at a real one, like one of the ones from the credit card number, or am I looking at just a piece of noise that just happened to be a 1? So if you take the intersection of those locations in each case, in other words, where there's a bold character in each one of the examples, that will kind of help you eliminate where the noise is and where the real characters are. So now we can look at one of the tokens that starts with 04 and see that, okay, the digits that appear in the original card number always show up in these positions, and the rest of it is garbage. And similarly, you can do that for the other mask indexes, let's call them. Okay. Since we know we're dealing with some sort of reordering here of the digits, because we didn't see patterns in our first card number, we got to figure out how are they ordered. And a credit card number with a bunch of 1s isn't going to help us figure out the ordering. So we generated a few more credit card numbers, and then went through that whole process of scripting it up, changing it in the database, and pulling out the ones that correspond to a similar mask index. So in this case, key index number 97. So we pulled all those out and looked at what resulted from 3 different credit card numbers: our original one, and then 2 more ones that we generated using that same tool as before. So now what we hope to be able to do is draw some sort of mapping between the digits in the obfuscated or reordered card number and the digits, the position of the digits in the original card number. And you could totally do this programmatically, but rather than writing that, it was easier to just mark it up on a graph. So what we're going to do here is see how the 4s are underlined in the second card number there. We're going to take those digits from the original card number, and the columns here correspond to the digits in the obfuscated card number, as underlined in green up there. So we're going to put an X anytime a particular digit appears at a particular position in the original card. So for example, the first one, a 4. A 4 in the reordered one appears at positions 1, 4, and 9 in the original card number. And then we have to do that for each one of the 4s in the reordered card number, just because we don't know which one of those is the right X. We're kind of laying out all the possibilities here. And we do that with the 0s as well. So a 0 appears at positions 2, 5, and 6 in the original card numbers. We put X's in those spots under the appropriate columns. So we do that for all